Good day, Justin Miller here, Oxnard College Physics. We are going to be looking at images formed by refraction for this session. So let's just get to it. We know that images are formed where either light rays physically intersect or where they trace back to a point of intersection after they've undergone some sort of redirection. We've looked at reflection, redirection of light rays due to reflection, and images formed by reflection for planar surfaces and for spherical surfaces. Then we're going to do the same sort of thing with refraction, because ultimately we can have a change in direction due to refraction and images formed. So let's just take a little for instance sort of thing going on to see what we're dealing with here. And surface boundary between two different materials. We'll say that this is air, where we've got some N sub A, index of refraction of air, and then let's take this to be water. And say that we've got some index of refraction for water, we'll just call it N sub W. So here's the interface boundary between the two materials, and let's take that there is some object immersed within this water. So I'm going to draw in sort of a principal axis here just to help us align stuff a little bit. I'm going to put some object, point object, on here. What we want to look at is the light rays that come off this object and then ultimately will go out into the air. So we have one obvious light ray that will go parallel to the principal axis, along the principal axis really, and then we'll enter and continue going onward straight, no change in direction because it struck the interface boundary at normal incidence. However, we got a bunch of different light rays as well, right? A cone of light rays that ultimately interface with this boundary. So let's just look at a couple. We can take another one that comes up like this. Well, when it strikes the mirror, strikes the interface boundary there, it is striking at some non-zero angle. We can just call this some theta 1, right? What's going to happen? Well, refraction is going to occur. According to Snell's law, N1 sine theta 1 is N2 sine theta 2. And mainly, what we want to get is the direction of this ray, what it looks like afterwards. So we are going from a higher index of refraction to a lower index of refraction. Thus the light ray will bend away from the normal, right? Stuff we've already looked at. So this light ray, by some amount, changes its direction. Great. We've got ourselves some theta 2 there. Well, if we look back, put our eye here, or put our eye there, where our eye is going to see this object, really the image of the object, is where the rays intersect. The rays that have to be tracing back, because these two rays on this side are never going to intersect. They're divergent from one another. So ultimately, if we trace this ray back here, we have an intersection point right there. That's where we're going to see this image to be located. So while we may be looking from here and seeing the image right there, really the object's much further away. If you've ever seen something submerged in water before and looked down at it, it looks like it's closer than it really is. You reach for it, oh my gosh, it's not there, it's way down here. And it's something that you can easily go test yourself with by just, I don't know, filling up a sink of water and putting a coin in there or something. Or swimming pool or bathtub, you can stay away from the toilet. Anyways, this is what we end up getting for all the light rays that ultimately come off of this. We got one that would come like this, and then come like this, such that it traces back to that location. You can take another one, it's over here, it doesn't refract as much. Does it look ugly? No, it's very bad, very bad. Erase that part. Do the same thing, fill this up. Everything traces back to be at that location where the image is located. This would give us what type of image? Real or virtual? That's right, this would be a virtual image. Refracted rays must trace back to a point of intersection. Refracted rays trace back. Well, what happens if we went the other way around? What if maybe we're in water and the object's out in the air? Let's see what happens with that. Let's reverse things around a little bit. Just leave that up for right now. So now we'll take this to be the water and this to be the air. And throw in a nice little principal axis here. That's again for helping align us. And we'll take an object that is initially in the air. It's going to be super helpful if it's not super straight. Take an object that's initially in the air. Okay, we've got an object right there. Again, we can look at light rays that come off of it. One goes along the principal axis and then keeps on going. No change in direction due to normal incidence. And then we've got some other light rays. We've got one that would come up like this, strike at some angle relative to the normal, which we can call theta 1. And then it undergoes some refraction. And now we've got something else going on regarding the direction that it goes into. The direction that it goes is towards the normal. We're going from a lower index of refraction to a higher index of refraction. Thus, the angle of refraction is lower than the angle of incidence. And we've got something like that. Well, what are we going to get in terms of intersection? Nothing's going to intersect on this side. We're still going to have divergence of the refracted rays as they exit the air and enter the water. But again, we'll still have that they trace back to a point of intersection. And that's where the image is going to be formed. Again, we could do this for any rays that we want that are interacting. There's another ray that does something like this, and then still bends in towards the normal, but it will be such that it is now aligned with that point there. And this still applies. No matter which way we look at it, with a planar interface boundary, we'll always get virtual images formed by refraction with a planar boundary. Now, other types of boundary surfaces that we could have, like spherical type of a surface. And we get some different things going on. But this is basically what we got for the case where we're just looking at planar boundaries. Pretty straightforward.